All right, so these are just some kind of tips for us, for things to think about. I'm going to always kind of work on the more complicated looking side to see if we can simplify. I try not to ever work both sides at the same time. It's a really good way to get scrambled in what you're trying to do. Pieces to try and watch out for. Look for things we can factor, add, subtract, square. Another good one to watch out for is a common denominator. See if we can get to common denominators. That's a comma. I'm going to put common denominator. Common denominator is a great one to watch out for. We're going to get to some stuff where we're starting to try substitution, because we may need to factor and substitute, and substitution helps with factoring. When in doubt, convert everything to sines and cosines. And then the last thing to remember when we're stuck is to just keep trying. Do a thing. Keep doing a thing. Okay? Don't give up, because I know you can do it. Okay? So we're going to do a bunch of verifying over the next 3 days. That's all of 7-1 is verifying. There's a very small segment of not verifying in 7-1. Okay? So we're going to be living back in the verifying plurals for a while. I'm going to give a second to keep writing, because no, I see a lot of people writing, and that's okay. So all those trig identities that we wrote down last chapter, yeah, those are going to come back too. So we're going to hit, I think we're going to hit all of them today at some point. Yeah, we should. We should hit all of them today. So it'll be a good refresher for us on that. Okay. So here's our first one. Got 1 plus sine of x times 1 minus sine of x. And we want to show that that equals cosine squared of x. So what's our instinct? What's our first thing we could do here? Yeah, distribute, multiply it out. This is a kind of double distribution situation where we're going to have 1 times 1 giving us 1. 1 times minus sine of x gives us minus sine of x. And we got to take our sine of x and multiply it out. We've got 1 times sine of x giving us plus sine of x. And that's an x. Minus sine squared of x. When I'm writing these, I tend to just get to the equal sign and stop because I'm trying to not work both sides. So I'm just going to leave this side blank because it's just the same thing being dropped down. I'm going to fix this x because that looks a little cray. There we go. Then what can we do? Yeah, I've got a minus sine x and a plus sine x. So those guys cancel out. So now what I have is 1 minus sine squared x. Oh, that's way chunkier. I don't know if I like that. I'm going to go back. Let's get it done. And here's where we're having our first trig identity of the day. Because we're going to remember on our trig identities, I'm going to put it up at the top. We had one of them that was sine squared plus cosine squared equals 1. So if I solve this one, so what does 1 minus sine squared equal? Cosine squared. So using that trig identity, this is the same thing as cosine squared of x. So cosine squared of x, and what our right-hand side was cosine squared of x. So we did it. My left-hand side matches my right-hand side. Those are both check marks. They were just trash marks. My left-hand side matches my right-hand side, so we did it. So I'm working one side. This side definitely looked like the more complicated side, and I got all the way down until it matched the right-hand side. Okay. Questions on this one? Because I know we got a little stuck on the verifying a little bit on the last chapter. Another one. You're gonna be living in these for forever. So we've got cotangent squared of theta times secant squared theta minus 1. All equals 1. You all right? What did... Oh, you're playing with your... Oh, playing with your leg braces. He was like, are you playing with Velcro pants? I'm like, what are you doing? It's okay. You're fine. It was just loud. So definitely this is the more complicated side. So we're going to be working the left-hand side. What can we do here? We could change cotangent into sine and cosine. We could change secant squared into cosine and sine. We could distribute. I think distributing is probably the hard way. Or there's a trig identity that we can use. So there's lots of ways to go through it. So we can do it with switching to sine and cosine. But that is also a hard way. The easy way, I'm going to put it up here, is to remember that 1 plus tangent squared equals secant squared. So that's the easy way. You could switch it to sine and cosine. There are about 6 different ways through each of these. Some of them are just going to be harder than others, and you're going to wind up with more steps. So these identities, that probably should have been like on one of our list of options. Check for an identity in here. Because this whole thing equals what? Tangent squared. So this is the tangent squared of theta times cotangent squared of theta. So check for an identity first. That's definitely the easy way. You can still do it. It was just going to wind up really messy. It's fine to go the other ways. It's absolutely fine. You're going to wind up with our sine over cosine squared. We'd have to multiply in. We're going to get all kinds of common denominators, and it's got to be a big thing. Doable, but a big thing. So once we're here, what can we do?
Cosine over sine times sine over cosine.
Yeah. We're going to put this into our sines and cosines because cotangent squared, so we're going to have cosine squared of theta over sine squared of theta. And tangent is sine theta, or squared, excuse me, and cosine squared over theta. What happens with my sines? They cancel. What happens with my cosines? They cancel out. So we're left with 1 equals 1. That was a clicking with the color-coded pens. That sounds like that when I do homework at home too. That's okay. Okay, so then we wound up with 1 equals 1, and we have, in fact, verified this. My left-hand side equals my right-hand side. So, again, there's about 8 different ways through it that I can think of off the top of my head. And they're not better or righter or wronger than any of the others. Some are more efficient ways through it with fewer steps. So if we can spot an identity and make it so I don't have to distribute and it's just multiplication, that'll save us some time. Because if I switch to sine and cosine up here, then we're getting common denominators and like it's going to be a whole thing. doable, absolutely valid, and 100% fine. It's just longer. Okay? So there are lots and lots and lots of options on how to do it. Next one. We've got cosine squared of beta. All of our Greek letters will make a turn back through. Minus sine squared of beta equals 1 minus 2 sine squared of beta. And one of the tricksy parts of this is getting each side to match up when this side seems super weird anyway. So what I notice over here is that everything's in sines. And over here I have a cosine. It's cosine squared, so that can be helpful with things. But I need it to be in terms of sines. So one approach for this is to get my cosine to become a sine is to think back to that trig identity, the one we wrote down first. Yeah. Our 1 equals cosine squared x plus sine x, which I entirely just wrote down backwards, but that's okay. Sine squared x plus cosine squared x equals 1. It's the normal way I write it. I have no idea why I wrote it the other way around, but I did. It was a choice. I made a choice. And we can rewrite our cosine into an equivalent piece here, because cosine squared of x is the same thing as 1 minus sine squared of x. They mean the same thing. I can prove it with this identity. Bless you. So I can come over here and swap this cosine squared out for 1 minus sine squared of beta. Minus sine squared of beta, and we're up to our equal sign. So I wanted everything to be sines, so I switched my cosine to be a sine. Now what can I do with this?
1 minus 2. We'll put them together.
Yeah, we're going to combine some like terms here. I'm going to make this pen a little thicker. I don't like it being skinny. Because I've got minus 1 sine squared of x, minus 1 sine squared of x. So I have 1 minus 2 sine squared of beta. I kept saying x, but I meant beta. Which is exactly what my right-hand side was originally. Just a weird looking thing. But all we care is that my left-hand side now matches my right-hand side. We had to go about it a weird way because I needed to switch them all over to be sines, but it's a thing. Okay, so make sure we pay attention to where we're trying to go. Where we're trying to go. Okay. Next one. So we've got tangent squared of alpha plus 4 and secant squared of alpha plus 3. So you're starting to get a little weird. But I see tangents and secants. So seeing tangent squared and secant squared at the same time should trigger a identity to pop through our head. Because we know a relationship between tangent and secant. I know 1 plus tangent of x, or tangent squared of x, sorry, equals secant squared x. That's one of those Pythagorean identities. Hello. There we go. So what can we do? Perfect. And you can do this on either side. You can either work the left-hand side or the right-hand side. I'm going to go left because that's the way you just said. Because that was, and what you also said. I heard you too. So we can take our tangent squared of alpha and turn that into secant squared of alpha minus 1 plus 4 that's based off of that trig identity, based off of this guy up here. Because now I have secant squared of alpha minus 1 plus 4. Wait, what can we do next? How do we finish it out? Because we're almost there. Are these parentheses actually doing anything? No. So what can we do to simplify it? Combine like terms. I have a minus 1 and a plus 4, which gives us secant squared of alpha plus 3, which is exactly what we wanted it to become. So my left-hand side matches my right-hand side. And it would 100% work the other direction to switch our secant squared out for tangent plus 1, and it would work 100% the other direction as well. I have 3 more for us to do today. They're slightly longer, but not that much. 3 more. Okay? All right. They start to get slightly messier. Because I have sine squared of theta minus sine to the 4th of theta. And we would like that to equal cosine squared of theta minus cosine to the 4th of theta. So I see sine and cosine both being raised to exponents. So we're probably going to need our trig identity. Our sine squared of theta plus cosine squared of theta equals 1. We're probably going to need this one at some point, way, shape, or form. What can we do? What's our instinct? If I need my sines to turn into cosines. Yeah. So I could absolutely take a sine squared and use the fact that sine squared is the same thing as 1 minus cosine squared. And I can switch this guy down into being 1 minus cosine squared of theta. This piece, isn't that just sine squared squared? So could I do the same thing but then just square it? So we're going to have our 1 minus cosine squared theta squared. And it's going to be like horizontally long here on the next line, just so we're aware. Because we going to square it. When we square it, and this is a mistake I've seen kind of repeatedly from several of us, remember that that means I'm taking my 1 minus cosine squared theta times 1 minus cosine squared theta. So I need to have a middle term as well, not just 1 squared and cosine squared. I'm gonna just write it all down. 1 minus cosine squared theta minus that whole thing. So we're gonna multiply out this whole piece here. 1 minus cosine squared theta minus. This is about to be real long because we have our 1 times 1, which is 1. 1 times minus cosine squared. So we have minus cosine squared theta. 1, my goodness gracious, somebody's group text is blowing up because their phone is buzzing every half a second. It's generally coming, I believe, from the right side of the room. But somebody's group text is blowing up. So then we've got our minus cosine squared times minus cosine squared to get plus cosine to the 4th of theta. And we're all the way up to that equal sign. Told you this is going to get wide. And we're going to be really, really careful because I have a lot of minus signs here. So my next step, I'm going to distribute this minus sign all the way through because holy cow, is this getting to be messy. So I have 1 minus my cosine squared theta minus 1 plus cosine squared theta plus cosine squared theta minus cosine to the 4th of theta. And we're up to our equal sign. Whew. What do we see? We've got some like terms to combine. What like terms do we have that can combine? I've got a 1 and a minus 1. So what happens there? Cancels. Yeah, I've got minus cosine squared plus cosine squared plus cosine squared. So how many cosine squareds do we wind up with at the end? 1 cosine squared of theta. And then I have my minus cosine to the 4th of theta. Which is, if we look way back up at the top, exactly what I wanted this thing to equal. Cosine squared of theta minus cosine to the 4th of theta. It's obnoxious, but it's there. So these things can get really long. They can become very, very fractiony, or they can become very, very wide. So some of these are a lot. Okay. 2 more. Now we've got cotangent cubed of theta over cosecant theta. And we want to know if that equals cosine theta times cosecant squared theta minus 1. And I see cotangents and cosecants, which is hopefully going to trigger our 3rd trig identity that we haven't worked with yet, our 3rd Pythagorean identity. The one that's used, honestly, probably the least. And that's our 1 plus cotangent squared equals cosecant squared. So I see cotangents and I see cosecants. And so I'm going to toss this one up there to help me remember. So I'm probably going to work with the right-hand side because honestly, I don't see much to do over here, whereas this one has things I see that we can do. So I'm going to work the right-hand side. Because what can I do over here on the right-hand side?
Make it cotangent squared.
Yeah, using that trig identity, this guy is the same as cotangent squared times cosine. So I'd like to get this cosine combined with my cotangent in some way, shape, or form. So let's maybe switch my cotangent into sines and cosines, because I'd like my cosine to join in the club somehow. So we have cosine theta times cotangent is cosine squared theta over sine squared theta. So we can multiply that together. That's going to give us cosine cubed theta over sine squared theta. And we're getting there. Like things are being all right. But I'd really like cotangent cubed. To get cotangent cubed, I need to have another sign here. So what I'm going to do is I'm going to multiply this whole thing times 1. But I'm going to make it be a really weird 1. Because I would like to have cosine cubed over sine cubed so I can get that cotangent cubed. So I need another sign on the bottom. But I can't just randomly multiply by sine. However, I can multiply by 1. Since I want to have cotangent cubed, I want 3 sets of cotangent, which means I need another sign. That lets me have cosine cubed theta over sine cubed theta. And we have an extra sign over here. I'm going to change the view real quick so you can actually see what's going on here. There we go. So it's not all at the bottom. I promise I'll zoom it all the way out at the end before we get to the next one. I did that because this guy now turns into cotangent cubed, which is what our goal is up at the top. We needed cotangent cubed up here. So I got my cotangent cubed, and now I have times sine. Another way of writing sine, think about our reciprocal. It's 1 over cosecant. Because cosecant is 1 over sine. So 1 over sine. It's like a double reciprocal. It's obnoxious, but it's a thing. And cotangent cubed over cosecant is exactly what we want because they're being pests. So cotangent cubed over cosecant is exactly this as long as we multiply by a 1 because they're being annoying. Because this is a 1. This is the way my brain did it. The other way, you can go through it this way and kind of try and simplify things. You'll still need this identity to get through with that -1 there somewhere. So again, there's lots of different ways to go through it. We got to kind of work on getting towards the goal that we have there. So this one has this super tricky, you have to multiply in a sine thing, and then our double reciprocal annoyance out here. I promise the last one for today is less gross. Okay, because we only have one more. One more, and it's less gross than this one. Okay, because this one was gross. This one was gross. To be fair, they get gross. They do. All right. So we have secant x minus cosine x, and we would like that to equal sine x times tangent x. And like I said, last one. This is the last. So when looking through this, when we're trying to figure out our strategy, I go, well, shoot. I don't see any squareds, so we don't have any of the Pythagorean identities. Because all those Pythagorean identities have a sine squared, a cosine squared, a secant squared, a tangent squared, somebody's squared. I don't have any squares here, so we're not working with one of them. So what can we do? Yeah. Oh, sorry. Got to change the view so you don't have to follow my brain. So we're going to switch these into being sine and cosine. So I'm going to work with the left-hand side because it's easier to play with the minus things and make multiplication than it is to go the other way. So I'm going to rewrite my secant as 1 over cosine. And I've got minus cosine. And what can I do with those? In order to subtract them together, what do they need to have? Common denominators. So what do I need to multiply this right hand by? Cosine over cosine. So we're going to wind up with our common denominator of cosine x, and my numerator is 1 minus cosine squared x. Now I see a cosine squared. 1 minus cosine squared actually equals sine squared, so we have sine squared x over cosine x. Our goal has a tangent in it, so let's split apart our sine so that we can make a tangent. So I can split my sine squared into being sine of x times sine of x over cosine of x. Sine of x over cosine x, also known as tangent. And that is exactly what we wanted it to be up on the top. Was sine of x times tangent of x. Okay? So our verifying is coming back into our lives. It's going to be here for a while. So here is the 7-1 homework. I will get you guys the printout of the whole schedule of the chapter next week, because I'm still working on making sure I don't give you any of the homework problems that I went you gross on the last chapter. So I am actually out tomorrow.
Yes. Oh, sorry.
Written there, not a surprise.
No, we got the
Chill.
Isn't it like after
Let me finish my sentence first, thank you. So I am out tomorrow. Boo hoo hoo. I know we're all very sad. And then Thursday's also e-learning. There's videos for the rest of this. They're already up. It's 4 videos. They're all about, they're less than 10 minutes. I just made like 2 or 3 problems in a video, so it wasn't one gargantua video. Mostly because I can't do them all right that many times in a row. Come on. So those videos are your assignments for tomorrow and Thursday. So if you want to do them all tomorrow and have no e-learning on Thursday, understandable. If you want to save them all and do them Thursday or over the weekend, you do you. So 7-1 is the assignment on this, and it's all verifying stuff. Okay? As far as the convocation for tomorrow, I have put in the request for you guys to go to the convocation because it is after 3rd period. They haven't told us yet who gets to go. So we'll see. But yes, it is after this period tomorrow, theoretically. So if you're working on stuff, as you're going through videos, going through notes, whatever you need to, if you have questions, send me emails. Feel free to text me. My number's on the little pink forms in the corners in every side of the room. I'm going to be at a training, so I'll have my phone and my computer with me. Okay? So, but since we're just starting chapter 7 and I'm trying to make sure we don't give you any more of those super gross problems, I will get the list of homework assignments to you when we come back from the long weekend, because I'm making sure that we don't have any of those problems again, because we had a couple of those last chapter that were really, really, really terrible. Okay?